Chapter 9, Lesson 4. And this lesson we'll talk about sigma and pi bonds. And essentially this is going to pick up from the previous lesson's ideas of hybridized and unhybridized orbitals. This is going to explain in a little more detail what the bonding looks like on the molecular level. So we're going to define two types of bonds. Sigma bonds. This is actually a Greek letter, the Greek letter sigma. And with sigma bonds, the electron density lies on the axis between the nuclei, which simply means if you have yourself this bond, so the sigma bond is the one that connects the two atoms together. So there's a bond that actually is between the carbon and the oxygen. That's your sigma bond. The pi bond, on the other hand, the electron density lies above and below the plane. And that's, these two atoms are actually also connected like this, kind of a weird way. They're actually connected above. There's two types of bonds in the CO2 molecule and in many molecules. There's your sigma bond, which is internuclear between the two nuclei, and then the pi bonds, which are above and below, is the idea. And there's actually another one coming up here as well. These are called pi bonds. Now, here it says that the second bond in a double bond and the third in a triple bond are pi bonds. So, if you have, for example, say this sort of molecule, which we'll take a closer look at in just a minute, for this carbon, its sigma bond is this guy, and its pi bonds, how about orange, are these two. Since it also has a sigma bond on the left, we'll see that carbon has two sigma bonds, and then it has two pi bonds. And that's the sort of thing we're going to take a look at. To take a look at a little more detail, pi bonds, if a molecule has pi bonds, then it cannot rotate, because the pi bonds essentially make it rigid and make it from moving or rotating. So these two carbons, for example, cannot rotate because of a double bond that exists, and the double bond actually makes the molecule have these pi bonds that are above and below the molecule. And because these are interacting, the molecule has to stay planar, or not planar, but it has to stay rigid, and it cannot spin. It has to be this sort of thing. Now, we talked about hybrid orbitals. So in this case, for example, if you take a look in the middle, what we have is we have an sp2 arrangement, which means we have 1, 2, 3 equivalent hybrid orbitals, and then we have an unhybridized p orbital. And when carbon bonds with another carbon, you can now see, here's the sigma bond. This is the internuclear bond. It has an sp2 trigonal planar arrangement, so one of them is in the middle. Same thing between the hydrogen and the carbon. And here are the other two. And the third one is this unhybridized p orbital that goes above and below. So study this in a little more detail, and maybe it'll make a little more sense, the difference between pi and sigma bonds. So we'll take a look at a few molecules. Here's ethylene, a fun-loving substance. And ethylene, if you count, has 5 sigma and 1 pi bond. Let's circle all the sigmas. 1, 2, 3. Remember, every single bond is a sigma bond, and the first of a double bond is a sigma bond. So all these are sigma. And then it has just 1 pi bond. In this case, this guy here is your pi bond. And if you visualize what this looks like, your sigma bonds are these sp2 hybrid orbitals. Here they are. They're between the two nuclei. There's a carbon nucleus here and the hydrogen. So these are coming between the nuclei, sitting between the one carbon and the other. And then your pi unhybridized orbital, the p, is the one that goes up and below. And so what happens is in the case of acetylene, actually, we're actually looking at a different molecule here, C2H2. This molecule looks something like this. A famous organic molecule. The C, the carbon here, is sp hybridized. And the sp hybridized orbital forms essentially two sigma bonds. the 2 sigma bonds are between hydrogen and carbon, and one between carbon and carbon. Here they are, 1 and 2. The other 2 unhybridized orbitals are 2 p orbitals, because remember you have sp3, so these are unhybridized, and they are the ones that make up this pair right here. And then this is the bond, because both carbons are equivalent, both carbons have the exact same picture. The connection between these unhybridized p orbitals are what we call the pi bond, is the idea. So study this picture a bit to see if it makes sense. A little more detail of the same thing. One pi bond is above and below, and one is in front and behind the molecule. Again, the reason for this is because in this molecule you have an sp hybridization and 2 unhybridized. The 2 unhybridized p orbitals, one is up and down, xy, one is in and out. So this is actually, think of this as y and then x. And these are your unhybridized p orbitals. By the way, this is always seen in triple bonds. So in the case of N2, for example, this is the picture that you see. N2, if you recall, has a triple bond between the 2 nitrogens. So this is, you got yourself this picture. You have a sigma bond and 2 pi bonds. This is especially interestingly seen in a molecule called benzene, a very famous molecule in organic and biochemistry. What happens in benzene? Benzene is a very strange molecule. It actually is a ring. There are molecules that actually exist as rings. And actually, let's try that again. If I were to draw this, there's going to be a carbon here, carbon there, like so. And if you try to follow the octet rule, what you'll find happening is you'll find this sort of thing happening. You have alternating single and double bonds in benzene. And each carbon, it follows the octet rule, and each carbon, if you take a look, has 3 equivalent 1, 2, 3 technically equivalent bonds, and this is called, we need an S and 2 p, so we call this sp2. So we leave one unhybridized p orbital. This unhybridized p orbital essentially is what you're seeing in this picture. Every carbon here has an unhybridized p orbital. So what will happen then, these p orbitals will combine together, as you'll see in a minute, and interact with one another. Just a little bit of amusement circling those p orbitals. And so here actually you see the hybridized sp2, 3 equivalent, 1, 2, 3 equivalent orbitals on each carbon, and then here are the unhybridized p orbitals left. So these p orbitals actually combine together to give you a picture that looks like this. All of them actually interact, all of them bond together. And this is actually experimentally confirmed, because the benzene molecule in organic chemistry actually does not react as though there are alternating single and double bonds. It reacts as though all of the bonds are equivalent, are the same. There's no difference between them, and we call this idea delocalization. This concept is readily applied to molecules that exhibit this sort of unhybridized p orbital character. So, now let's get some general conclusions. Every 2 atoms share at least 2 electrons. We knew that from the start. 2 electrons between atoms on the same axis are sigma. This is between 2. This is your internuclear bond. Sigma bonds are always localized, means they cannot go anywhere in the molecule. They have to stay between the 2 nuclei. And then if 2 atoms share more than a pair of electrons, this is in the case of double and triple bonds, these become pi bonds. And by definition, pi bonds are unhybridized. So if 2 atoms have pi bonds, these can then delocalize and go between the 2 atoms. So the idea is sigma bonds cannot delocalize, they are localized, but pi bonds delocalize, creating this pi structure above and below the molecule. So why don't we try to determine how many sigma and how many pi bonds in the molecule below. The name is allene. Wouldn't that be a nice name to name your daughter? A perfect name, allene. And so what we have in this case, recall that every single bond is a sigma bond. So here's a sigma, here's a sigma, here's one, and here's one. The first bond of a double bond is a sigma. The second bond of a double bond is a pi. So total we have 1, 2, 3, 4, 5, 6 sigma bonds and 2 pi bonds. As easy as this. But it's also a good idea to be able to visualize what happens with these orbitals. There is, in fact, on every carbon here, an unhybridized p orbital. One on this one, one on this one, one on this one. And again, that's because each carbon here is sp2 hybridized, because you have 3 electron domains. So you leave an unhybridized p orbital on every single carbon. So this molecule actually exhibits delocalization. These bonds are able to delocalize and go all over the molecule, and that's kind of the idea. So I believe this wraps up our lesson and the whole chapter, chapter 9.